Gradient descent and variance. Gradient descent. Description. Gradient descent is an iterative optimization algorithm used to minimize the cost function of a machine learning model by adjusting its parameters iteratively. Steps. Calculate gradient. Description. Compute the gradient of the cost function with respect to each model parameter. Update parameters. Description. Update model parameters in the opposite direction of the gradient to reduce the cost function. Iteration. Description. Repeat the process until convergence or a predefined number of iterations. Variance of gradient descent. Batch gradient descent. Description. Computes the gradient of the cost function using the entire dataset. Updates parameters after evaluating gradients for the entire dataset. Characteristics. Pros. Converges to the global minimum with smooth cost function simpler to implement. Cons. Computationally expensive for large datasets, requires memory to store the entire dataset. Stochastic gradient descent (SGD). Description. Computes the gradient of the cost function using one random instance or a small batch from the dataset. Updates parameters after evaluating gradients for each instance. Characteristics. Pros. Faster convergence due to frequent updates, handles large datasets well. Cons. Noisy updates can cause fluctuating convergence, may require tuning of learning rate. Mini-batch gradient descent. Description. Computes the gradient of the cost function using a small random subset mini-batch of the dataset. Updates parameters after evaluating gradients for each mini-batch. Characteristics. Pros. Balance between batch GD and SGD in terms of convergence speed and computational efficiency. Cons. Requires tuning of batch size, less noisy updates compared to SGD, but can still exhibit oscillations. Momentum gradient descent. Description. Enhances SGD by accumulating a velocity vector of gradients to accelerate convergence through momentum. Characteristics. Pros. Faster convergence through accumulated momentum smooths out oscillations in SGD. Cons. Requires tuning of momentum parameter, may overshoot minima in some cases. ADA-grad adaptive gradient algorithm. Description. Adapts the learning rate of each parameter based on the historical gradient updates. It decreases the learning rate for frequently occurring parameters and increases it for infrequent ones. Characteristics. Pros. Automatically adjusts learning rates effective for sparse data. Cons. Learning rate can become overly small over time, may stop learning prematurely. RMS prop root mean square propagation. Description. Optimizes ADA-grad by using a moving average of squared gradients to normalize the learning rate. Characteristics. Pros. Adaptive learning rate per parameter, effective for non-stationary problems. Cons. Requires tuning of decay rate, may accumulate momentum too aggressively. ADAM adaptive moment estimation. Description. Combines the benefits of momentum and RMS prop by using both first-order moments mean and second-order moments in centered variance of gradients for adaptive learning rates. Characteristics. Pros. Efficient convergence with adaptive learning rates, handles noisy gradients and sparse data well. Cons. Requires tuning of momentum and decay rates, may converge prematurely in some scenarios.